first example of the day that we are going to work through is determining the percent composition for each of the elements, carbon, hydrogen, and oxygen, inside of table sugar. So we have sugar, which the formula is C6H12O6, also pictured down below. So what we're going to be doing is figuring out what the percentage of carbon's contribution is to the mass, hydrogen's contribution to the mass, and oxygen's percent contribution to the mass. Now, if you are working along at home, again, please take a pause, try and use our previous equation to determine the mass percent for yourself. But if this is after the pause, then welcome back. Let's use that equation to figure out what the mass percent composition for each of these elements in the molecule is. All right, so our equation, just to go backwards, has two different parts that we're trying to figure out, right? Either the numerator's component or the denominator's component. Times 100 is always going to be times 100. So we are looking for the total mass of an element in the compound, and we're looking for the total mass of the compound. So let's actually start with the denominator. It's going to be the easiest thing to look for because we've actually already found this type of thing before. The total mass of the compound is going to be equal to the formula weight of the compound in the unit of AMU. So we're going to take all 6 of our carbons, all 12 of our hydrogens, and all 6 of our oxygens and add all of the masses together. 6 times the mass of our carbon on the periodic table is 12.01 AMU. We're going to take that and add it to 12 times the mass of hydrogen on the periodic table, which is 1.008 AMU. And we're going to add that to 6 times the mass of oxygen on the periodic table, which is 16.00 AMU. We crunch these numbers in our calculator, and what we find is that the total mass of our molecule is going to be around 180.2 atomic mass units. So this is going to be what we place in the denominator of each of our mass percent calculations. So I'm just gonna block that off down here, and we have all of the rest of the space up here to crunch the numbers for the carbon, the hydrogen, and the oxygen. All right, so we still have to find, though, the numerator for each of these calculations. Well, what the numerator is meant to represent is the total mass of an individual element's contribution to the total molecule. So in carbon's case, there are 6 carbons inside of this molecule, meaning that its contribution to the mass is going to be 6 times 12.01 atomic mass units. So literally, basically what we're doing is we're going to take carbon's contribution to the total mass down here and just put that into the numerator and divide that by the whole, which is 180.2 AMU. And then of course times by 100. But if we continue to set up the rest of these elements before crunching these numbers, we can really see this pattern. Hydrogen's contribution, we can see also down below, 12 times 1.008 AMU, all divided by that 180.2 AMU. And again, percent, so times by 100. And oxygen's, we can see last. It's that 6 times 16.00, all divided by 180.2 AMU. And again, all times 100. So we can see that each of these individual pieces from our calculation of the total mass just get broken up and placed in the numerators corresponding to each individual element that we're focusing on. So carbon's comes first, hydrogen second, oxygen third, and now we have 3 individual calculations for finding the mass percent contribution of each of these elements inside of table sugar. All right, so carbon, we crunch these numbers, we find that its percent contribution to the mass is 40.0%. Hydrogen, coming next, is 6.71%, and oxygen, coming last, is 53.3%. So carbon may only be 6 of the atoms inside of this molecule, but it contributes 40% of the weight. Hydrogen, in great contrast, may be half of all of the elements present inside of this molecule, but in terms of mass, because hydrogen is so incredibly light, it's only 6.71% of all of the mass that's found inside of table sugar. Oxygen comprises the majority of the mass because it is the heaviest of all of the elements present inside of the chemical.